Hi, and welcome back to the Learning Circuit. Getting information from the real world into our technology requires converting analog and digital signals. In some situations, to get those signals back out, they need to be converted again. For this, we use a digital to analog converter, or DAC. Let's take a look at how to build one and see how it works. In my previous video, the lesson about DACs, I explained that the more efficient version uses what is called an R2R ladder. What that means is that it uses a lot of resistors of the same value. Two of those resistors in series in the cases of 2R, structured in a way that breaks multiple inputs into a binary sequence. Given the layout of the resistors, each input is weighted for a binary digit, each representing 1 bit. The more inputs, the more bits. The more bits, the higher the resolution, the more accurate the conversion from digital to analog. With the R2R structure, each input connects to 2 resistors, giving the value 2R, which in turn connects to a series of R value resistors, with each input connection dividing that series. For our test circuit, each input will be one of the Arduino digital inputs. The beginning of the resistor series gets connected to ground, while the end of the resistor series allows us to view the output wave. For this demo, I need an Arduino Uno, a USB cable for programming, a breadboard, a bunch of jumper wires, and a whole lot of resistors of the same value. On my breadboard, one resistor will straddle the rows, with another connecting and running perpendicular. Right now, that's RR. So I'll add a second resistor connecting in the top set of rows to give us a value of 2R. And that resistor will connect to one digital Arduino input. To add another bit, I repeat this resistor placement. The first junction of these new resistors will also connect to the loose lead of that first perpendicular resistor. Okay, that gives us a 2-bit digital to analog converter. That's not very useful, so let's keep going and add more bits. I'm using the digital I/O on the Arduino. While there are 14 of these pins, I'm only using 12, so that's how many bits worth of resistors I need to add. Okay, I'll add 2 resistors in series to the beginning and end of the ladder as shown in the schematic. That connects the beginning to ground and the end of the series to analog input A0 on the Arduino. That's it for the hardware. Let's take a peek at the code we need to make our DAC work and see the output. I got most of this code from a project in the Arduino.cc project hub, so credit to the original authors. There are some minor tweaks and additions to the original code. For example, I'll be showing different resolutions by changing the number of inputs we use, so I added these constants to help keep track of the maximum number of bits possible. Next, we create a variable that can be used to create the output sine wave, and the baud rate is set to 9600 per usual. I had to look up how to use this next bit of code, so I'll do my best to explain it. Let's look at the port manipulation reference page on the Arduino site. Port registers allow for lower level and faster manipulation of the I/O pins. With 3 ports B, C, and D. I want to use pins 0 through 11, so I need ports B and D. Scrolling down, I want a data direction register for ports D and B. Scrolling down further, we can see how to set each pin to an input or output using binary numbers. Back in our Arduino code, we have DDRD equals B for binary, followed by 8 bits. The least significant bit is pin 0 and up through pin 7, each marked 1 to set it as an output. Then DDRB with 6 bits for the remaining 6 pins. We want to use pins 8 through 11, so pins 12 and 13 are marked 0, making them inputs. That's it for setup. Let's take a look at the program loop. We start with a for loop that generates a sine wave. The values are broken up by the bit resolution which we set up earlier. Now, when we go to look at the sine wave this generates, the steps may not be perfectly even. Due to the 1% variance of the resistors, the value of each 1K resistor can be plus or minus 10 ohms. If they were exactly the same, the steps would be identical. Port D can only manage 8 bits, so assign the first 8 bits as low bits, then take the next 4 bits from port B and assign them as high bits. Then shift over the high bits by 8 to put them in their proper place for a complete 12-bit number. And as usual, we add a short delay to help keep the code running smoothly. We include serial print dialog so we can see the output without an oscilloscope. Now, I actually want to start at a low resolution and work our way up to show you the differences. So let's bump this down to 4 bits. Okay, send that code to the Arduino. And I need to move my jumper to the 4th bit place for the resistors. And I'll open the serial plotter to see our 4-bit sine wave. With this very low resolution of only 16, you can clearly see the steps. But it's not very sine-y, is it? Let's bump it up to 6-bit, a resolution of 64. Change my code, push it to the Arduino, adjust my jumper to 6, and let's look at the serial plotter. Now the wave is much smoother than the 4-bit, but the steps are still very noticeable. Let's bump it up to 8-bit, a resolution of 256. Change my resolution to 8, send it, move my jumper. Let's look at that plotter again. Now this wave looks much more like a true sine wave. While the line is still a bit jagged, the smooth shape is clear. This resolution could be sufficient in a lot of applications that have slow changes. Last, let's bump this up to our full resolution, 496 at 12-bit. Change my code, send it to the Arduino. Move my jumper, full 12 bits. Let's see what that plotter looks like. Ooh, it's so smooth and sine-y. Look at that. Here, the steps are nearly imperceptible. Now, unfortunately, the serial plotter doesn't have a pause or a stop function for us to take a closer look. However, I can take a screenshot and zoom in. Here, if we zoom in on the wave, you can see that there are still tiny steps. We can compare a screenshot of each example to clearly see the difference resolution makes. Most analog output waves are created from input waves that were originally analog, but first converted to digital. Remember that no matter how high the resolution, that original analog signal has been compressed somewhat into digital and can never be returned to truly analog again. There's always going to be some steps in that output signal. Well, I hope you enjoyed my DAC digital to analog converter demonstration. I encourage you to try it at home. One thing I often do is hook up my output sine wave to lights or a speaker to get a more tangible feel for what that wave will be like in the physical world. This time, I want you to do that. So hook up your circuits, try different resolutions, try different frequencies. Report back with your findings about how using different bits affects the light and sound output. Post your results on the Element 14 community on element14.com/the learning circuit. I look forward to seeing what you find. Happy learning!